Have you ever wondered what truly happens in the milliseconds between pressing the power button and seeing your Linux login prompt? It's a complex yet elegant dance of hardware and software, often taken for granted, but absolutely critical to system stability and performance. Understanding this sequence is not just academic. It gives you the power to diagnose boot failures, optimize startup times, and even harden your system against threats. In this deep dive, we'll unravel the intricate stages of the Linux boot process. We'll start with the initial hardware checks, move through the bootloader's role, explore kernel initialization, and finally, look at how the init system brings your operating environment to life. By the end, you'll have a clear, actionable understanding of this fundamental OS operation. The journey begins with the firmware, either the traditional BIOS or its modern successor, UEFI. When you power on, the CPU first executes code stored in this firmware. BIOS performs the power-on self-test, or POST, checking essential hardware components. UEFI, on the other hand, is more advanced, offering features like secure boot and faster initialization. Once the hardware is validated, the firmware's next task is to locate a bootable device. For BIOS, this typically involves reading the master boot record, MBR, or guide partition table, GPT, on a disk. UEFI directly reads boot entries from an EFI System Partition. This initial stage then hands control over to the bootloader, a small program specifically designed to load the operating system. Think of the firmware as the usher and the bootloader as the stage manager, preparing the main act. Once the firmware passes control, the GNU Grand Unified Bootloader, or GRUB, GRUB, takes center stage. GRUB is incredibly flexible, capable of booting various operating systems and even supporting complex boot scenarios. It presents a menu, allowing you to choose which kernel to boot or even pass specific boot parameters. After your selection, GRUB's primary role is to load the Linux kernel image and an initial RAM disk, known as initramfs, into memory. The kernel is the heart of the OS, but it often needs drivers and modules to access root file systems and other hardware, especially early in the boot process. This is where initramfs comes in. It's a temporary root file system containing essential tools and modules. The kernel then executes a program from initramfs to mount the real root file system, and once that's done, it transitions control to the init process on the persistent root file system, marking a significant milestone in the boot sequence. Now that the kernel has taken over and mounted the root file system, it's time for the init process to bring the system fully online. Modern Linux distributions primarily use systemd, a powerful and complex init system. Older systems might still use SysV init, but systemd has become the de facto standard due to its parallelization capabilities and extensive features. Systemd's first job is to bring up the core services needed for a minimal operating environment. It does this by reading unit files, which define services, sockets, devices, and mount points. It then resolves dependencies and starts services in parallel, significantly speeding up boot times compared to the serial execution of SysV init. Consider a large-scale data center scenario, thousands of servers booting concurrently. The efficiency of systemd's parallel service startup is paramount here. It ensures that critical services like networking, databases, and web servers are available quickly and reliably, minimizing downtime and maximizing throughput across the entire infrastructure. This shift from serial to parallel execution is a cornerstone of modern system performance. We've journeyed from power-on to a fully operational Linux system. The boot process, while robust, is constantly evolving. One significant trend is the increasing focus on secure boot, a UEFI feature that ensures only trusted software loads at startup, mitigating rootkits and other low-level attacks. We're also seeing the rise of immutable operating systems, where the core OS file system is read-only, simplifying updates and enhancing security by preventing unauthorized modifications. Innovations in bootloader technology, like systemd aim for even faster and more streamlined boot sequences, especially in cloud and containerized environments. The key takeaway here is that optimizing and securing the boot process is an ongoing challenge and opportunity. For systems programmers, a deep understanding of these stages is your foundation for building more resilient, performant, and secure systems. Keep exploring, keep learning, and remember that even the most complex systems are built on these fundamental interactions. Thank you.